Hello, everybody. It's Mrs. Pound, and we're still working on chapter 1.2 about the nature of matter. And our next topic is gases in section 1.2.5. We've already covered solids and liquids, so now we're on to gases. And our objectives today are to identify some properties of gases, to apply kinetic theory to the states of matter. We've already done it with solids and liquids, and to predict the behavior of gases according to Boyle's law and Charles's law. So a gas is the state in which matter does not have a definite shape or a definite volume. So I have some balloons in the background there, and the balloons are there to show you that gases, we fill balloons with gases, take the shape of their container and the volume of their container. They will fill up the whole container. So the molecular structure and how it relates to the properties of a gas. Number one, remember we have three things for each one. Gas particles have more energy than solids or liquids. Remember, for solids, they're vibrating in place. For liquids, they're able to flow over one another, the particles, but for gases, they are flying all over the place. In fact, there are gases flying all over the room you're in and the room I'm in right now, bouncing off of everything, a lot like billiard balls. That's why I have the picture of the billiard balls in the background. They will fly in a straight line till they hit the side of the container they're in, then they will fly back in a straight line until they hit another wall and keep going, just like billiard balls. The second thing about gases is their greater motion allows the particles to overcome cohesion. They're not attached together like solids and liquids. And we also tend to, your book doesn't talk about this, but we tend to talk about gases as if there are ideal gases. Ideal gases have no attraction between the particles. Now, real gases do tend to, but ideal gases do not have any kind of attraction between the particles in them. And the third thing is they have no definite shape or volume, which we kind of already talked about, and that's why I have the balloons in the background again. So another thing we need to know about gases is we tend to measure their pressure. This is the amount of force exerted on an object per unit of area. And so I have that little manometer, that pressure gauge in the background to remind us of that we can measure the pressure. You've probably done this yourself or watched your parents measure tire pressure. That's a common pressure of gases that we measure. And so this is the force exerted on an area. It's the force of the gases exerted, say, on the walls of the tire, on the walls of a balloon, on the walls of whatever container it is in, pushing those walls outward. Now, Boyle's law is probably something new to you. However, the concept is probably not new. Boyle's law says the volume of a fixed amount of gas at a constant temperature increases as its pressure decreases and decreases as its pressure increases. And we see this with a syringe. Now, this is my syringe here that I found at my house. This syringe isn't a very good syringe. I apologize that it's not going to show this principle all that well, but I'm sure you've played with this syringe before. And I'm sure you have taken your finger and you've capped one end and you've pressed that syringe, and you notice that as you press that syringe, the volume here goes down and the pressure increases. You can feel that. Okay, so as the pressure increases, the volume down here decreases. And if I let go of the pressure, and this is where my syringe isn't very good, usually that plunger pops right back out. So if I decrease the amount of pressure I'm putting on the syringe, the volume will increase. Okay? So that is Boyle's law. There's also a law called Charles' law. And this is the volume of a gas at a constant pressure increases as its temperature increases and decreases as its temperature decreases. We see this with balloons and tires, so I'm going to look at those two examples. According to Charles' law, does the mass of gas change in a balloon when the temperature changes? I'm sure you have gone outside on a cold day with some of those balloons like I have in the background, especially the foil balloons, and notice that your balloons shrank. So does that mean that they've lost air, they've lost mass? No, the pressure changed. The molecules started to slow down and were not moving as much, and so they were putting less pressure on the balloon. And then I'm sure you've taken those same balloons, and when you go back into the room, okay, a warm room, they expand again. That's because the molecules have warmed up, they're moving faster, they're bouncing harder against the walls of their container, their pressure has increased. So the pressure changes, not the mass. This is also what we observed going on with our thermal expansion experiment that we did in class with the Erlenmeyer flask and the balloon on top that I put in the ice water and then in the boiling water. And we saw with the ice water, the balloon was limp. When I put it in the hot water, it stood up because of the increased pressure from the molecules hitting the walls of the balloon. And another question that applies to this has to do with tires. It says, why does air pressure in a tire change when air temperature changes? Maybe you have noticed or your parents have pointed out that in the summer, you might have to take a little air out of your tires. That is because the temperature affects the tires. Likewise, when temperatures get colder, you might find that you have to put air in your tires because of Charles's law, which shows the molecules move faster if the temperature increases, increasing the pressure. So this is the case in the summer. The molecules are moving faster because the temperature increased, increasing the pressure, so we might have to let a little bit of air out of our tires. And also, the molecules move slower if the temperature decreases, decreasing the pressure. In the winter, we might find that our tires are a little soft and we have to add some air because the molecules are moving slower and they're not hitting the sides of the tire walls, with as much force. And so that is how Charles' law applies to tires. So our objectives today were to identify some properties of gases. We talked about pressure. And to apply kinetic theory to states of matter. We talked about, with the kinetic theory, all particles in motion are in motion that are in matter. In solids, vibrating back and forth in place. Liquids flowing over each other. Gases zooming all over the place, okay? And we also predicted the behavior of gases according to Boyle's law and Charles' law. Boyle's law applies to our syringe, and Charles' law applies to balloons and tires when they change temperature. So we'll continue on with this chapter about talking about phase changes when these states of matter go back and forth. And don't forget your 5 questions that you have to write.